So a scalar, which we're pretty used to, is any quantity that's described only by a number. And it's often described with units. It's almost always described with units because that gives meaning to the number. So we have, for example, I've written here, temperature is 21 degrees Celsius, or the time was 5.81 seconds. And just some general examples of scalars would be time and temperature, which we've just seen, or things like density, mass, volume. These are all scalars. Now, a vector is a little bit different than a scalar. A vector, oh, that's nice, is any quantity that is described with both magnitude, that means size, and direction. This is very important. The direction makes it a vector. So you might have seen in the past, we have velocity, and for an example, that would be 21 meters per second east. So the speed is 21 meters per second, and the direction is east, so velocity is 21 meters per second east. Or force, 210 newtons, and then west. Now some examples, general examples of vectors are force, velocity, acceleration, all the kinematic kind of quantities that you're used to, displacement, momentum, impulse, electric field, magnetic field. These are all examples of vectors. Now, it would be useful to understand how to work with vectors if we're going to be doing some physics. So, say I have a general vector, we'll call it A. General vector called A. And I'm just on a Cartesian coordinate system here. So I have x and y. All right, so maybe here's my x, and this is my y-axis. So my vector A, so any vector is always described with an arrow. As you can see, I have this arrow here, and it has the end of it here, and the arrowhead of it up here. And this describes my vector A, right? And I write the vector with a little line over top to indicate that it's a vector. Now, what does this mean? This means that my vector A, at the point where the vector starts, the value there has a certain magnitude, which is this length here, and also this direction. And the direction is very specific because it points exactly, in this case, in this direction. So, some important qualities of vectors. One is that a vector, as long as it keeps its direction and its size, its length, I can move that vector wherever I please in my Cartesian plane. Wherever I like, doesn't matter. Okay? It's often we choose our coordinate system so that our vectors will start at the origin, which just makes our life nice and easy. Okay, and that's the arbitrariness of a coordinate system. You arbitrarily choose the origin to be somewhere that's convenient. Okay, and because of the fact that we can basically drag and move vectors around, say I have another vector B, and they're both at the origin, and I want it to know what is the vector sum of those two. So I might ask, what is, we'll call it R, the resultant, such that we have A plus B. What does that look like, and how would I find that? So one way we can do that is graphically. What I can do, because I can slide my vectors anywhere I like, I can take B, and I can slide its feather end, not its arrowhead end, up to there. So I take the tail of B, and I put it at the tip of A. Okay, we'll call that the tip to tail. So tip to tail method. So I can take B, and because I can move vectors anywhere I like as long as I don't change their magnitude or the direction, I can take the tip of B, the tail of B, and put it at the tip of A. Okay, so then my resultant vector, R, this guy here, would be the vector that starts where A starts and goes to where B ends. So let's use black. If it starts here, oh, that's red, and goes there. So start here and goes there. Okay? And that would be my vector R, resultant R. So, what is that effect? That effect is essentially I have started at the origin, I moved along A, and then once I finished moving along A, I moved along B, and I ended up at this point here, right here. Okay, and that has the same effect as if I started at the origin and moved along R until the end of R. I would end up at the same point. Okay? Now, we should be able to notice that there's a very important property here, and it's called the commutative property. So if R is A plus B, then it should also hold true that it's also B plus A. So what does that mean? If I take B and I put it back where I found it, I started at the origin, and now instead of adding B to A, instead of taking this one and putting it here, I'm going to do the opposite. I'm going to take A and I'm going to put it here. So let's see what that looks like. So if I grab A and I slide it using the tip to tail method, what I should get is the exact same thing. So again, I have started, it says if I started at the origin and I moved along B until it ended, and then once I was there I moved along A until it ended, I get out here at this point here. Okay, and that has the same effect as if I started at the origin and I moved along R, the resultant vector of adding B to A, and or A to B, and I end up here. Now you might notice because of this property here, this commutative property, that I can basically make a nice little parallelogram with my vectors. So if I double up, I grab A and I clone it. Clone, there it is. And then I grab it and I put it here where it started. And I do the same for B. And I grab it and I put it here. You'll notice because of this commutative property right here that I get A plus B which is that, is the same as b plus a, which is that route, and they both yield the resultant r vector. And it gives me this nice, lovely parallelogram that I've got here.